do that.
Show that I sine squared of x cosine squared of x is not linearly independent.
There's new ones on that board over there.
Oh. Sorry. Here's a better pen. There are two ways. One is to use the Wronskian. What's a Wronskian? You write these functions. And you write their derivatives until you get a square matrix. You can't compute the determinant of a matrix that's not a square. If you are given some matrix and you want to compute its determinant, it has to be a square matrix, meaning the number of rows, the number of columns should equal to number of rows. Since I have 3 columns for 3 functions, I better have 3 rows, right? That means I have to differentiate 2 more times, okay? You differentiate this once, you get 0. Differentiating again, you get 0. Differentiating sine squared of x gives you what? 2 sine x cosine x. Differentiating this gives you negative 2 cosine x sine x. And then differentiating this again, well, you need to use the chain rule. That gives you, not chain rule, sorry, product rule. Differentiating this gives you cosine, so it's cosine squared of x minus, when you differentiate cosine, you get negative sine, so you get negative 2 sine squared of x. And over here, when you differentiate cosine, differentiates to negative sine, so it's 2 sine squared of x minus 2 cosine squared of x. So now we have a 3 by 3 matrix. That's a square matrix. Therefore, we can compute its derivative, compute its determinant. By the way, when you have a matrix with this bar there, that means it's the determinant of a matrix. Usually, this is the matrix, and if you do this, that means the determinant of this matrix. Okay? Please, you should distinguish between those two symbols. Okay? I've noticed some students using this when they mean the actual matrix, and just this when they mean actual determinant. Okay, you have to distinguish between them. Okay, now let's try to compute the determinant. How do you compute the determinant? You do either the row expansion or a column expansion, right? And it is wise to pick the row or the column that has the most zeros. See, I have 2 zeros on the first column, so it's better to expand with respect to this column. And it's done in three steps, right? So first step is you write down these elements that you run into, pi 0, 0, pi 0, 0. And then you multiply the minors. And the minors are what you get if you deleted the row and the column containing the element that you picked. Okay, so I picked pi, that means I delete this, and this is what you get. So, 2 sine x cosine x. I need more space, just a minute. Done. 2 sine x cosine x minus 2 cosine x sine x. 2 cosine squared of x minus 2 sine squared of x. 2 sine squared of x minus 2 cosine squared of x. And then the next one is 0 times the minor matrix that you get after picking this one is this, right? Because you're deleting the row and the column, and that's what you're left with. Yes?
Like on the test to save time, since we already know the zeros in the front, can we just cancel it out?
Yes,
and
of
solve
course,
the
of
bottom
course.
of it?
Yeah, I'm just trying to explain what's going on, but if you know that this is going to be 0, because 0 times anything is 0, so you don't have to write this. Okay, so 2 cosine squared of x, 2 sine squared of x, 2 sine squared of x minus 2 cosine squared of x. Okay. Plus 0 and I'm tired. Okay, and then the next thing that you have to apply, the third step is to apply the checkerboard of signs. What's the checkerboard of signs? It's like the checkerboard's made up of plus and minuses. So here's it. And you always start with the plus on the top left, okay? So that has to be applied, so it's plus, minus, plus, okay? That's how you compute a 3×3 determinant. Or 4×4, you just repeat this process. If you have a 4×4 matrix, then you start with expansion, the minors become 3×3, and that can be expanded again. So you can always compute any size determinants this way. Now, as you can see, these are all zeros, so that doesn't count. And then over here, if you do this times this, minus this times pi, you're going to see that it becomes 0. So let's check. Pi, this times this, that's 2 times 2, that's 4 sine x, cosine x, sine squared of x, minus cosine squared of x, right? And over here, I can, because I'm subtracting, minus becomes plus, and 2 and 2, so it's plus 4 sine x, cosine squared of x, minus sine squared of x. And if you put them together, since this is common, you can factor this out, and after you factor it out, you see that negative cosine squared of x plus cosine squared of x becomes 0, so these two cancel. And then sine squared of x and negative sine squared of x, they cancel. If you choose to expand and add them up, you see that everything just cancels and you get 0. Now, if the Wronskian becomes 0, what does that mean? It's linearly dependent. Okay. If it's not equal to 0, that's the proof that they're linearly independent. If they're equal to 0, that means they're dependent. Okay. All right. Here's another solution that doesn't require Wronskians. Solution 2. Being linearly dependent means that there is a K1 plus K2 plus K3 equal to 0 for some constants K1, K2, K3. Now, we already know that 0, 0, 0 would always work, but if there is a set of numbers, K1, K2, K3, which are not all zeros, which satisfy this equation, then it means that these three functions are linearly dependent. It means dependent. Okay? Independent means that this can only happen if all of K1, K2, K3 are 0. Okay? All right, so our goal is, if I want to show that they're not linearly independent, meaning that if I want to show that they're linearly dependent, my goal is to find these values, K1, K2, and K3, which will make this work. Well, start with this. Sine squared of x plus cosine squared of x equal to 1. So I have, if I multiply by pi, here's what I have. pi times sine squared of x plus pi times cosine squared of x equal to pi, right? I multiplied it by pi because then I can have this. Now I move this to the other side and I get negative pi plus sine squared of x plus cosine squared of x. Oh, sorry. Plus pi times sine squared of x plus pi times cosine squared of x equal to 0. So I got this relation. Compare this with what we want. Compare these two. Then did we find K1, K2, K3? K1 must be negative 1. K2 must be pi. K3 can be pi. So we found 3 numbers which will make this equal to 0 without all, not all of them being 0. So other than 0, 0, 0, we do have a solution. Yes?
I have a quick question. Now,
Yes.
when you get left, like for 1b, when you do like Wronskians for that, and you're left with x values, what are you supposed to do? Like, if it's technically not equal to 0, or
Right.
do you have to solve?
Okay, let me do that afterwards. Okay, so you got this? Okay. All right. So those are the 2 ways to show that a given function is linearly dependent. Here's another example. How about x plus 1 and x squared? What about these? Yes?
Why would K1, so K1 is equal to negative 1, K2 and K3 equal to pi?
Yeah.
Why would that mean it's dependent? Like,
That's the definition of 3 functions being linearly dependent.
okay,
There's a linear relationship between them.
okay.
That's what it means. Okay? Dependent means there's a linear relationship between them. Why do we care? We care because when we try to solve differential equations, we want unique solutions, right? So when we write down, so let's say you have a differential equation, see, our method of solving differential equations for higher order is you don't solve it, you make guesses, right? But because we are making guesses, we have to justify what we do, right? And one of the things that you have to justify is that if I had 3 different solutions for a 3rd order differential equation, I have to say that, oh, these 3 are genuinely different kind of functions. They're not related to each other in any way. So if I make them into C1 times the first, C2 times the second, plus C3 times the third, and make a general solution, I found all the solutions. That's what I want to say. But for that to work, I really need to show that there is no linear relationship between the 3 functions. That's the reason why we're doing this.
K2 and K3 equal to pi. That means there isn't a unique solution, right?
So hypothetically, think about the following. Let's say you have some y triple prime plus something, y double prime something, y prime something, y equals to 0, and we're trying to solve this, right? Homogeneous 3rd order. And let's say we did trial and error and found out that the solutions we found were like, I know pi is a solution, sine squared is a solution, cosine squared is a solution. And then now I say, oh, look, I found 3 solutions. Now let's write down the general solution. Y equals to C1 plus C2 plus C3. And you're ready to say, okay, we found everything. Let's do another one, right? But then the other guy will say, not so fast. Why? Because you seem to claim that these are 3 different functions, but really, because sine squared plus cosine squared is 1, you can create this other function from these. In other words, look, pi is pi times sine squared of x plus pi times cosine squared of x. If pi can be represented as this, then think about what would happen if I replace this pi by this thing. What's going to happen? I can now multiply this out and write it as c1 pi plus c2 sine squared of x, c1 pi plus c3 cosine squared of x, and then this is just some function, some constant, that's just some constant. So you really found 2 degrees of freedom here, c1 and c2. What does that mean? That means this is a third order. You better have three degrees of freedom to find the unique solution for all possible initial conditions. But you failed. What does that mean?
There is another solution.
There's another solution. You have to go out and hunt for another. Okay? That's why this question of whether it's independent or dependent is very important. Okay? All right. So, actually, that was a good question because I need such a discussion for this next question. See, I skipped this theorem, but there's a theorem in the textbook which says, suppose you have a second order differential equation where this is a constant, could be something other than 1, but it has to be some constant, and then you have px y prime plus qx y equal to 0. Suppose you have a homogeneous differential equation like this, and you found 2 solutions, y1 and y2. Then the theorem goes as this. If the Wronskian, what's the Wronskian in this case? To get a square matrix, you have to differentiate, right? Now we have a 2 by 2, so we can take the determinant. If this is not equal to 0 for just one single value, then it is never equal to 0 for any x value. See, y1, y2, although I wrote it like this, these are functions of x, right? And when you take the determinant, that's still a function of x. Therefore, you get a function of x, which may give you 0 for some value and not 0 for other values, right? But the theorem says if this y1 and y2 happens to be a solution of this differential equation where px and qx is not singular, meaning that it's always defined, it's continuous, in that case, once 0, never 0. That's what it means, okay? And vice versa. If it's 0 at just one point, for one single value, it's always 0. Okay. So whether 2 functions are linearly dependent or independent is very clear in this context, right? It happens, however, this kind of theorem is not guaranteed if this has something like, let's say x plus 1 or something like that, so that this can be 0 for certain values. See, if x is -1, this will be 0, right? In that case, such a theorem doesn't hold. And that's what happens to this solution. You will never be able to find this pair of solutions when it's of this form. Okay? But if there's something in here which makes the coefficient singular, then you may have something like this, which means at some points you can't say they're linearly independent, and that's the issue here. But these are too theoretical, and I didn't want to raise this as a big concern. I just wanted to show you how to compute the Wronskian for this one and deduce their linear independence for this. Okay, so what's the Wronskian in this case? The Wronskian of 2 functions, x plus 1 and x squared, is you simply make a square matrix out of it. Since we have 2, you just have to differentiate once and then take the determinant, because you have 2 by 2, you can take the determinant. And it's this times this minus this times this. Okay, so it's x plus 1 times 2x minus x squared times 1, which is 2x squared plus 2x minus x squared, which is x squared plus 2x. Now for this one, you see that there are 2 points where these two functions could be 0, x equal to 0 and x equals to negative 2. In this case, the proper way to say it is that thus the two functions are linearly independent for all values of x other than x equal to 0 and negative 2. Okay? So other than this, they are linearly independent. Okay? And what it really means is that your differential equation will have the highest order term vanishing at these points. When x equals to 0 or x equals to negative 2, it's going to vanish. And thus, temporarily at these points, this second order differential equation at x equal to 0 and x equals to negative 2, suddenly this term vanishes at those points, leaving you with this first order differential equation. In that case, it's impossible to find two linearly independent solutions that are linearly independent for all real numbers. Okay, that's what's happening. Okay? So there's some theoretical thing behind it, but for exam purposes, you don't have to go to this much depth. Just say, oh, this is non-zero, so they're linearly independent. I'll give you full credit.
Sure. Now, how come it wouldn't be dependent for 0 then? So they're both.
I mean, the intuitive way of thinking of it is that because y double prime suddenly vanishes at these points, the differential equation will be like the first order, in which case you will only be expecting one solution rather than two solutions. So you see, for second order, you would expect two linearly independent ones. For third order, you would expect three linearly independent ones. But temporarily, there's a change in the order of this differential equation, so you fail to have this linear independence there. So that's like a very tiny point there, which I didn't want to make it a big issue, but that's what's happening. All right. Is this doing a method of undetermined coefficient would include some form of